Hey, this is notes, the back page for 5.4 exponential function base e. Example 9, find the extrema and points of inflection for g of t. We have to think about curve sketching, first and second derivative tests. So we need to get to g prime in order to determine the critical points, and from there we can test each interval. Here, notice again, we have to go through product rule, and I'm going to leave it in this form. So 1 becomes 0. Notice 2 plus t and e to the negative t. These are two separate terms. I'll treat these, and they're being multiplied, so we have to go through product rule. So 2 plus t's derivative becomes 1. So f prime g plus f g prime. So the derivative for e to the negative t is e to the negative t times negative 1. We can move the e to the t to the denominator, and we have common denominators then. Combine the like terms up in the numerator. 1 minus 2 is negative 1 minus t. So we have our g prime of t being negative 1 minus t over e to the t. To find critical points, we have to consider numerator and denominator. So denominator e to the t equals 0. That's never going to happen. No critical points here. This graph is never going to cross the x-axis. Negative 1 minus t, if we set that equal to 0, we get t is equal to negative 1. So we have our critical point being at negative 1. And this could be a potential max or min, but to determine that, we're going to have to test values on each side of the derivative, each side of the critical point. And we plug a value to the left of negative 1. Let's choose negative 2. So we plug negative 2 into the derivative. So negative 2 gets plugged in for t. Negative 1 minus 2 minus a negative 2, which is positive. Positive over positive. So we know the graph is going to be rising to the left of negative 1. If I plug in 0, I get negative 1 minus 0, which is negative, over a positive, which is negative. So we know the graph will be falling to the right of negative 1. So based off of this, we know the graph is rising, hits a maximum, falls. So we know relative maximum occurs at negative 1 as the x value. Now to find the y value, we have to plug negative 1 back into the original equation. And when we do that, we get 1 plus 2 minus 1 times e to the first power, so 1 plus e. So our relative max is a y value of 1 plus e. And because f prime changes from positive to negative would be our justification for our relative max. Okay. Points of inflection comes from second derivative, so we get to g double prime. Once we get to g double prime, find the critical points. Then we go through sine line again and test each interval. So here is g prime of t, negative 1 minus t over e to the t. So we have to go through quotient rule here. So f prime g minus f times g prime all over g squared. We can clean the numerator up a bit. Negative e to the t plus e to the t plus t e to the t. The e to the t's cancel out. We can cancel one of the e to the t's out in the numerator and denominator, so we're left with t over e to the t. Again, critical points, we have to consider both numerator and denominator. E to the t, again, will not produce any critical points. T, set that equal to 0, we get t equals 0, so our critical point for our potential points of inflection will be at t equals 0. So now we're going to test values to the left and to the right of our critical point. So negative 1 being a value to the left of 0, we plug negative 1 back into the second derivative. So if I plug negative 1 in for t, I'll get negative over a positive. Denominator is always positive. E raised to any value will remain a positive. So negative over positive is negative. To the right, if I plug 1, I'll get positive over a positive. So we know the graph is going to be concave up to the right. So concave down followed by concave up. And we know this point exists, so 0 must be a point of inflection. Now to find the y value of the point of inflection, we have to plug 0 back into the original equation. So the original equation is 1 plus 2 plus t times e to the negative t. So replace all the t's with 0. We get 1 plus 2 times e to the 0, which is 1, or 1 times 2, which is 2. So 1 plus 2 is 3. So our ordered pair for point of inflection is at 0, 3. And our justification because f double prime changes signs. Okay, example 10, find the extrema in points of inflection. So again, consider the first and second derivative test, first derivative test and the concavity test. So with our function here, I'm going to clean this up a little bit to allow for us to have something that's a little bit easier maybe to find the derivative, so we don't have to deal with these negative exponents and potentially complex fractions. So e to the x minus 1 over e to the x, I'm going to convert the e to the negative x to positive exponent. Here I can find a common denominator. So I get e to the x as a common denominator for a numerator all over 2. So I'll have the 2 share the denominator space as e to the x. So this will be a little bit cleaner here. We're going to apply the quotient rule to find the first derivative. So f prime g minus f g prime all over g squared. Clean the numerator or expand the numerator to combine like terms. We get 4e to the 3x minus 2e to the 3x plus 2e to the x. These two combine like terms. We can factor the e to the x out. Once we have that, we can cancel out with the denominators e to the 2x. So we're left with e to the 2x plus 1 all over e to the x. Critical points, again, can come from numerator or denominator. But if we set the denominator equal to 0, again, no critical points here. If we set the numerator equal to 0, we get e to the 2x plus 1 equals 0. E to the 2x equals negative 1. Now we know that e to the exponential function is never going to be even able to cross the x-axis, much less go to a negative value. So we know this does not exist. So no critical points. So basically, if we can test any value, we'll be able to determine what the slope is. So the slope is always going to be either positive or negative. So basically, any value I plug in, if I plug in 0 into my derivative, I'm always going to get a positive value. So this function is always positive. So I know that my graph is always rising with no relative extrema, no increase, always increasing, no relative extrema. F double prime. To get from f prime to f double prime, we have to go through quotient rule again. So f prime g minus f g prime all over g squared. Expand the numerator out to combine like terms. Again, 2e to the 3x minus 2e to the x. Factor out the 2e to the x. Cancel with the denominator. We're left with e to the 2x minus 1 all over 2e to the x. Again, consider numerator and denominator for critical points. Denominator will not produce a critical point, but the numerator, we're going to set that equal to 0 and see what we get. E to the 2x minus 1 is equal to 0. E to the 2x is equal to 1. Take the natural log of both sides. Once we have that, the 2x can come down in front. Natural log of e cancels out. Natural log of 1 is 0. Solve for x, we get x equals 0. So our critical point is 0. Plot that on a sine line. We test a value to the left of 0, which is negative 1. Plug negative 1 into the second derivative, and we're going to get a negative over a positive, which is negative. If I plug in a positive 1, e to the 2 is larger than 1, so that's positive over positive, so positive value. There's a change in sign, so we know concave down followed by concave up. We know point inflection will occur at 0. Now to find the order pair, we're going to plug 0 back into the original equation. So e to the 0 is 1 minus e to the negative 0, which is 1. 1 minus 1 is 0. 0 over 2 is 0. So point inflection occurs at 0, 0 because f double prime changes signs.